This is the seventh and last video on directional properties of crystals. In this video, I'll discuss aggregate properties, in particular aggregate elastic properties, and I'll use the feldspars, the plagioclase feldspars, as my example. So, aggregate properties. How do you determine the elastic properties of a rock containing anisotropic crystals? Now, the beginning of this is to assume that you have porosity and crack-free aggregates. And we can imagine conceptually two extreme cases. Let's imagine a rock consisting of two crystals and that the strain is the same in both crystals. So these are two crystals of the same material. They could be different material, but let's imagine we have a b-axis of the crystal aligned in the blue crystal and the c-axis aligned in the green crystal. We apply strain to these crystals by depressing them downwards. So both crystals have been exposed to the same strain, and there is some average force divided by the area of the two crystals that is applied in order to accomplish this strain. So there's the measure of strain, and the stress will be the average of the two stresses in the two crystals. Well, the stresses are proportional to the elastic constant times the strain. So in this case, averaging the stiffnesses will allow us to calculate the stress associated with uniform strain. We'll call this the Voigt average, and in the Voigt average we accept the idea that an aggregate contains anisotropic materials that all experience the same strain. Now let's change it to the same stress in all crystals. In this case, imagine those two crystals with different crystallographic orientations aligned in parallel like this. Now when we apply a stress, sigma, which will lead to some strain as shown, the major point here is that both crystal faces are feeling exactly the same stress when they are aligned in parallel like this. So we have the same stress in both crystals. It makes sense now that we look at strain as proportional to some compliance times the stress. We need to, for constant stress, average the compliances. We'll call this the Royce average. The two averages will give us different estimates of the elastic properties. And the two averages, the two bounds, the Voigt and the Royce, represent two physically unrealistic situations. You would imagine that in a real crystal with all the green boundaries in contact that you have some mixture between uniform stress and uniform strain on the crystals. Hill's idea was to average the bounds provided by the Voigt and Royce estimates and to call this, and we now call this the Hill average. We can average in a variety of ways. A simple arithmetic mean is probably as easy as any other. Now there have been other estimates to consider the properties of an aggregate, and in particular Hashing and Strickman suggested a variational solution to the problem of mixed aggregate materials. Now this variational solution has tighter bounds than the Voigt and Royce, but is computationally more complex. I do have Fortran programs that allow calculation of the Hashing-Strickman bounds, and I have compiled them to run with MATLAB. However, the compiled version only runs on the same operating system of MATLAB, so it's a little bit awkward to pass that along. So now let's consider isotropic average properties of plagioclase. I do provide you with a MATLAB function called Voigt-Royce-Hill, VRH, using capital letters. And if you type in a output of K and G for bulk modulus and shear modulus and execute the Voigt-Royce-Hill function, passing it the matrix of elastic constants, this function will return a vector of K and a vector G. The K vector has the Voigt as the first, the Royce as the second, and the average Hill as the third element, likewise for G. We can apply Voigt-Royce-Hill averaging to the elastic constants determined for the plagioclase series feldspars, and I plot here values of bulk modulus and shear modulus as a percent anorthite, going from albite on the left to anorthite on the right. The black circles with error bars represent the elastic constants that we measured from the surface wave constrained by the compliance data. The error bars represent both statistical uncertainty, well, they represent the statistical uncertainty in determining the elastic constants. The black lines, the upper and the lower, represent the upper being the Voigt and the lower being the Royce bounds, and I've connected the Voigt-Royce bounds by lines, and you'll see that, in fact, albite is the most anisotropic. It has the widest Voigt-Royce bounds. At the intermediate composition, the Voigt-Royce bounds tighten up and then expand only slightly as you go to pure anorthite. Now, the X-ray compliance measurements provide a measurement of the bulk modulus, and the open squares are the X-ray measurements from Ross Angel's laboratory. They were used as a constraint in fitting for the elastic constants, and as you can see, the X-ray data follows along the Royce bounds, as they should, since in the X-ray single crystal experiments, a uniform stress was applied to the entire surface of the crystal. The shaded lines are Hashing-Strickman bounds. Now, Hashing-Strickman only is implemented up to monoclinic symmetry, so I in fact had to average the triclinic constants into monoclinic constants before then applying Hashing-Strickman bounds. You can see on the lower part the shear modulus, and notice here that the bulk modulus changes a fair amount with composition, whereas the shear modulus has only a very modest change in value from anorthite to albite. Again, you can see a widening of the Voigt-Royce bounds for albite narrowing to anorthite. These bulk modulus and shear moduluses can be used to calculate elastic wave velocities. Oh, I forgot to push the button and show you the legend here. And the compressional velocity is the function of bulk modulus and shear modulus, and the shear velocity goes as the shear modulus. In this diagram, the circles are measurements on rock aggregates that are all or almost all feldspars. These come from a variety of sources. The largest data set for the compressional velocities is from the famous paper by Francis Birch in 1961. Additional work by a number of authors have added a few more points to this diagram, as well as the shear wave velocities. So you can see that the compressional wave velocities measured in rocks increases from albite to anorthite, whereas the shear wave velocities only change a very small amount, going from albite to anorthite. I've plotted on there a shaded region which represents our estimates based on the Hill average, with the width representing the uncertainty based on the statistical fit to our elastic constants. The black lines represent the estimate from the Voigt, or the dashed lines represent the Voigt and Royce bounds, and the black lines, solid lines, represent the Hashing-Strickman bounds. So you can see Hashing-Strickman bounds lie within the Voigt-Royce bounds. all of the data lie within the Voigt-Royce bounds, and in fact the data all seem to lie within their uncertainty, agreeing with the Hill average of the single crystal elastic constants. Let me emphasize that up until this data set, there has been a long-standing controversy in the community in which rock physics measurements did not seem to agree with the Russian, the 1964 vintage plagioclase feldspar data. In fact, it had led a number of people to suggest either that the pseudo-single crystal data had a systematic bias, or that in fact the Voigt bound was preferred to the Royce bound in estimating aggregate properties. Using the correct values of the elastic constants gives us an estimate, in fact, that is in perfect agreement with the rock physics estimates. So the rocks, aggregates of crystals, and the single crystal data are in perfect agreement, and in fact the Hill average seems to work. So now let's talk about preferred orientation. This is a case in which the crystals are not randomly oriented, but rather have a preferred orientation, sometimes abbreviated as LPO, or lattice preferred orientation. How do you estimate lattice preferred orientation? Well, the first step is to get the orientation matrices, the orientation of individual crystals within an aggregate, within a rock, and you need enough orientation matrices to form an ensemble, a statistical sample of the crystals. Now, the given elastic constants or stiffnesses for the crystals, one would rotate the compliances or stiffnesses according to the orientation matrix, one rotation for each orientation matrix. You could average the collection of matrices rotated according to their orientation, and if you averaged the stiffnesses, you'd get the Voigt average, or if you averaged the compliances, you'd get the Royce estimate. Then one can calculate velocities as a function of direction in the rock using this average matrix. Let's go through again the issues with feldspar. Feldspar is ubiquitously twinned. The left-hand diagram shows the typical twinning according to the Albite twin law. And I'll note that the composition face is 010, and the twin axis is the C-axis. You simply flip the crystals around the C-axis. So to average a single domain within a rock, one could average, according to the Albite law, to take triclinic constants to monoclinic. Now, within the rock itself, you see in the right-hand figure that most of the crystals lie with a similar orientation for the B-axis. The A and C form a girdle. So let's first consider how to calculate the monoclinic anisotropy using MATLAB. So we want to average to monoclinic. So here's a MATLAB script to do that. First of all, let's feed in the elastic constants for Albite. You'll notice I've done it on 2 lines because with 21 constants it got pretty long, and we use a dot dot. Actually, there should be 3 dots there to indicate a continuation of the line in MATLAB. Now we need to make Cij using, in matrix form, you could use the function make Cij, and this again is just a test that you've correctly entered your constants and they form a matrix as you expect. Now, in order to average to monoclinic symmetry, actually we only need 2 crystals, a primary crystal and one rotated 180 degrees about the C-axis. And the C-axis and the Z-axis are only a few degrees apart, so I'm going to just substitute a simpler rotation about the Z-axis. So here's a Z-axis rotation. It has the three lines. Whoops, I'm missing a space between a 0 and 1 in the last line there. Now we get rotated elastic constants by taking that transformation matrix and operating on Cij. Now we simply add together the two elastic constants and divide by 2 to form their average. So here's the results. I'll show you from top to bottom. The top Cij is our initial primary orientation of the elastic constants in the chosen coordinate system that we reported the elastic constants. Remember, in triclinic minerals, none of the axes are at 90-degree angles, and you're free to choose any coordinate system you want, and we've simply chosen a convenient coordinate system that has some connection to the internal structure. The second 6x6 matrix is the rotated version of the elastic constants, and the last CAV is the average of those two. And if you count them up, there are 13 independent elastic constants. There are a lot of zeros in there. Now, because of the way we've done this, we've formed an alternate version of monoclinic constants. If you remember in the past video, the non-zero monoclinic constants were in the 5th row and column. Here they're in the 6th row and column because of just how we've defined the rotations. They're still equivalently a monoclinic description of the material. So I label it monoclinic. Now let's consider what happens when you have an ensemble of crystals that are aligned on the B-axis, and the A and C axes simply form a girdle about B. Okay, to get an appropriate average, I'm taking a set of angles for rotation about B, and I'll take it in 1 degree steps from 0 to 359. Now the length of this vector I can obtain with that command. I can set up an elastic constants matrix by saying zeros of 6, 6, so that's 6 deep and 6 wide. Now we simply loop over all of our angles of rotation. We determine a rotation matrix. This is our transformation matrix. It's a rotation about the B-axis. And we have, as usual, the sines and cosines of the angle. Now the average is going to be obtained by summing these various rotated matrices, and so we rotate it and add it to the previous value of C. We end this loop with the end command, and then we divide the outgoing constants by the total number of samples, and that gives us the average. We perform that on our crystal, and here's the result. And you'll see now that there are 5 elastic constants associated with the hexagonal symmetry, or alternately called transverse anisotropy. So let's look at how those constants behave as a function of direction. So on the horizontal axis, we have an angle measured from the girdle of A and C axes on the left to the unique direction, the B axis, on the right. Velocity is plotted vertically from 3 kilometers to over 8 kilometers per second. The lower set of curves are for the shear waves, and the upper set of curves for the compressional wave. The solid lines represent our estimates based on the current elastic constants. The dashed lines represent what you would get from the earlier Rysova elastic constants for the Albite feldspar. As you can see, the current data show a greater anisotropy, and in fact in the B-axis much higher velocities, over 8 kilometers per second compared to just a little over 7 for the Rysova elastic constants. You also see a larger variation of shear velocities at the intermediate directions. So it's at these intermediate directions that seismologists would see a large amount of shear wave splitting in a rock dominated with feldspar crystals having this degree of lattice preferred orientation. Now, how do these compare with rocks that show a lattice-preferred orientation? Well, it turns out that in 1993, Sarant and others published a set of velocities measured in a rock with a lattice-preferred orientation, and they reported not only the velocities, but they reported velocities in various directions within the rock, from a direction in which you are in the girdle direction to a direction in which the single crystal's b-axes are aligned. And as you can see, I've plotted their actual data, and on the equatorial girdle and at the b-axis you see perfect agreement between estimates from our current set of elastic constants. Those are the dashed lines showing Voigt and Royce, and in between dashed line is the hill. The lower curve represents one of their estimates for the elasticity of their rock. As you can see, for the most part, our elastic constants are in perfect agreement with the variation of velocity as one goes from propagation in the equator to propagation in the polar direction. There are a couple shear velocities that are not quite in accord, and I don't know whether that represents experimental error or something else, but they're not consistent with the behavior of transverse anisotropy under any stretch of the imagination. Again, the velocities on the girdle and along the b-axis are perfectly confirmed by the elastic constants we use. Now, in that paper, they noted that they could not get a fit between their measurements and the measurements of Rysova for the elasticity of plagioclase, and they attributed that to either a problem with the elastic constants or possibly a problem with schemes to average aggregate properties. I think here we have increasing evidence that the Hill average is a reasonable approximation for the properties of an aggregate of single crystals. That brings to a conclusion the set of lectures that I'm giving on directional properties of crystals. We've covered a lot of ground over the course of these 7 lectures, and I encourage you to go back to the initial outline to review what it is that I intended to cover. Thank you very much.